Hi, this is the second lecture in the set where we're going to be discussing Chapter 3 of Cummings and Kaufman, basically about electromagnetism and telescopes. In the book, there's a lot of reference to light as a wave, and very little in discussion about light as a particle. And there is really this duality going on in nature, especially with electromagnetism. To remind, there are the four forces in nature: gravity, electromagnetism, the strong and the weak, nuclear forces. What we want to talk about now is the evidence that we really have that light behaves as a wave and a particle. And as an idea of coming attractions, not only does light behave as a wave and a particle, but that electrons and protons and you and me also have wave-like characteristics. Now, what is a wave? What is a particle? And that's one of the major topics we want to get into here. I have this chart here that indicates a couple of ideas here, at least for light. We have the idea of Huygens principle, which we'll talk about later, very soon. And then we have this idea of superposition and interference. You're probably more connected or familiar with the idea of interference, especially things like noise-canceling headphones, echoes, and things like that. But there are, not only do we see it in terms of waves that we see and hear, but also this occurs with light. And so there are a couple other things I want to show you in that regards, and that's diffraction and polarization. And then finally we want to talk about light as a particle, and that is evidenced by what is called the photoelectric effect, and I have a video showing you an example of this. I do show an example of this in class, but I guess a video is going to have to do. Huygens' principle is basically this idea that if you drop something and you drop something in a lake, you create a set of waves, and you can visualize the creation of additional waves by building the new wave crest from the past wave crests. And so the idea is this here. Here is the original wavefront, or if you will, the crest of the wave. And what you do is you take a compass and you create a bunch of new waves which are created from the old one. So here is a dot here indicating where you put the point of the compass, and here's what you put the pencil. And then you keep on doing that, and then this new wavefront is the locus of all of the little compass marks you've made from this original wavefront. And so you really had a source up here, and then this wavefront propagates away from that source. Now you probably have seen waves, going around in water, and we have instruments that allow us to take a look at this in physics classes. I don't have such a device, but I remember one in high school. I didn't recognize what it was for. But the idea is that you can see how waves propagate going through little holes in walls, and depending upon the size of the hole, you'll have a different formation of the waves out in this region here. And if you look carefully here, the waves seem to be coming in, the waves are parallel to each other. You see a line of waves here, and then another one there, and another one there, and you're interested in how the wave propagates through this region here. And what you see here, if the hole is large enough, then the wave is unimpeded. That's sort of what you would expect. But out here, notice when you get close to this obstruction, that the wave sort of turns and sort of fills in the space. And this characteristic is amplified the smaller the hole becomes. So here we still have some plane wave characteristics, but here we have a really small hole, and the wave is just generated as if there was a source right here creating the waves in the very, to start with. And that's what we call interference. Okay. Basically, two waves can occupy the same place and the same time. And what we do to find out what is actually going on is we just add them together. And they can add, as I say here, either constructively or destructively. And an example of this in a physics experiment is called the Young double-slit experiment. And in a sense, it conclusively proved that light is a wave and not a particle. Up until that point, and actually afterwards, there was a big discussion about if it was either this or it was that. Now let me remind you what a wave and a particle is. Okay, a wave, if you will, imagine yourself in the ocean. A wave is a crest and a trough, and as you're sitting in the ocean, and this is beyond the beach break, okay, you're just bouncing up and down, and your movement is just that, mostly caused by you. Yes, you do go up and down, but you don't go sideways and you don't go into the shore or out of the shore, right? There are other effects that are going to do that. But you basically go up and down, and your position doesn't change very much over time. The wave has energy, and it goes through you, but doesn't really affect you. Okay, that is a wave. A wave, if you will, is dispersed, and it takes energy from one location to another. On the other hand, consider a particle. Particles hit things, and they bounce off of each other. So imagine again that you're in the ocean, bouncing up and down. Yes, you are a particle, and another particle comes up, a jet ski, and you have a collision. Collisions between people and jet skis aren't really good ones to have, but you get the idea, hopefully, that there is a lot of motion going on and that you get bounced around when such an event happens. Remember, that's the difference between a particle and a wave. The wave goes through you, doesn't interact very strongly with you at all, and goes on its merry way. Okay? The particle, on the other hand, if you get hit by it, you feel it. All right, so basically the idea here, if I can refer to the chart again, is only waves exhibit interference. Okay? Now, if we have superposition, and I just talked about what it was, the idea is that I can have, say, two sources, and in the places where the two waves are overlapping each other, I can create places where they're going to constructively interfere, and the size of the wave is deepened and made more shallow, right? So I have constructive interference both in a positive sense and a negative sense. Positive things become more positive, negative things become more negative. And then in the intervening regions, I kind of have destructive interference, where the high point of one wave matches up the low point of the other one, and I have flat water here. And you can see that, you know, it radiates out, and it's very geometrical in origin. Okay? Remember, geometry and math, that's how I keep score. All right? So what I want to show you now is some videos of some simple ideas, of these simple ideas. And let's see if these things play. And let's go and open up the hyperlink. And it looks like it's going to select, it's going to be allowing me to do it. And look at that, success. So notice the waves are going around the object. Let's see, look at the diffraction over here. Look at the diffraction of the waves going around this obstacle. Plane waves on the left-hand side, and then you see the diffraction behind the object. Now, let's see if we're successful with the next one. And in this particular video, notice where the waves, the two waves are separate and they come together, and where the wave is actually higher. It's as simple as that. I like looking at the ocean. I like being in the ocean. Now you can create simulations with these things as well. I'll show that as a final example. So again, in order to create a simulation, you have to use mathematics. Okay, it looks like I was unsuccessful there, so let's continue on. Okay, so that is with water waves. What happens when you have light waves? The same thing happens. You can create a light here. You can create an experiment where you start with, say, monochromatic light here, say, for example, an incandescent lamp or something like that, and then you shine it in a box, right? So you don't have light spilling around the corners, and then you shine it through two slits. According to our theory, at least with water waves, as these two slits will now be a source of two, if you will, two flashlights, and these two flashlights will then interfere with each other. Now, mind you, if you bring one flashlight and then a second one right next to it, you're not going to create these interference patterns. What you need to have is a parallel wave front coming across here, and flashlights don't have that. But what you can do is get a little card and use an X-Acto knife and put two small holes or two small slices in the piece of paper and then shine a light through it. That works, okay, and that's an experiment you can do and try it out, okay. And naturally, if you make a video of this that I could use, that's worth extra credit points to me. Okay, so let's see if we can get these movies to play. I guess you can see that the other one was there too, I just didn't recognize it. Okay, so this is an old-time physics movie. Here they're showing you the apparatus.
An increase in the distance between the two slits is accompanied by a decrease in the distance between the adjacent maxima. A decrease in the distance between the two slits is accompanied by an increase in the distance between the maxima. A decrease in the wavelength of the light is accompanied by a decrease in the distance between the interference maxima. An increase in the wavelength of the light is accompanied by an increase in the distance between the interference maxima. The double-slit interference pattern disappears.
Okay, so that is basically what we're talking about when we are talking about interference. Now you can do this yourself with lasers and with mechanical pencil leads, and I want to show you a video of that, and I've done this before too. Instead of pencil leads, what I do in class is I have a couple lasers, and the lasers have three different colors: violet, red, and green. And what I do there is I go, instead of round pencil leads, I use a paper clip. So this is something you could try at home too, with the same caveats as I had. See, look at the pattern developing. See the picket fence? You have to be really, really steady. It's hard to make this work. That's why I like to use paper clips. Okay, now it turns out that you can actually have light interfering with itself, and that's called diffraction. Examples of this are it basically limits our ability to see small things. So you know, it's similar to when headlights get too close together, and why eagles can see more clearly. Okay. Diffraction gratings is another thing that one can play with, and that is basically creating a lot of multiple slits. Okay, and we can see that with CDs, for example, or peacocks and things like that. So there are a lot of things out there that use diffraction. Okay, so here's diffraction again, and if you look at, say, an object with light, you know, of varying sizes, it can sort of the object can disappear, and we can have this bending effect going around it. If you have light that's smaller and smaller and smaller in size, and what I mean about that size is the wavelength of the light, then the image becomes more precise. The edges become more definitive. You can see this effect by, for example, going outside on a sunny day and holding up a quarter. The sun's rays are not parallel. They have some angle associated with them, and because the sun has some distinct size to it, we see it as a disk. And if you hold the object, the quarter, very close to where you're creating the image, say for example the ground, you have a very, very sharp edge to the shadow. And then as you move further and further, you move the quarter further and further away from, say, the sidewalk, you see that the edges become diffuse until finally you can't even see the quarter at all, even though the quarter is in your hand. All right, so if we will, let's take a look at single diffraction, or single slit diffraction, using our these old style movies. So it's the same setup as before.
An increase in the width of the slit is accompanied by a decrease in the distance between the adjacent dark regions or nodes. A decrease in the width of the slit is accompanied by an increase in the distance between the adjacent dark regions or nodes. A decrease in the wavelength of the light is accompanied by a decrease in the distance between the nodes. An increase in the wavelength of the light is accompanied by an increase in the distance between the nodes.
Now the term nodes here is just the region in between the bright spots, so it's the dark regions. Okay, so diffraction basically causes movement of the waves around objects or obstacles. And it's that thing that creates shadows and the fuzziness of the shadows, if you will. And that causes a limitation on how we can utilize, say, for example, telescopes. Okay, polarization is another effect, not so significant for us in our discussion here, but be aware that electromagnetic radiation waves can come in two different types, right-handed polarization or left-handed, and it has to do with how the actual fields are oscillating. And there's a picture here of polarization. If you polarize the light coming through an object, so for example sunglasses or the screens of the windscreens of cars, you can decrease the amount of glare by orienting the polarization on the screen such that you knock out some of the random light. So here we have two screens that are polarized in the same direction, and then here we're crossing them and the light doesn't go through. Now what's fun to do is you insert this third one that's sort of canted, and in this middle region you can see the person in the background there, but here and here and here you don't. So it's very curious about what's going on with the polarization as it goes through each one. Okay, so let that be something for you to think about, just the whole craziness of the natural world. All right, now now I promised you that there are other effects that light behaves as a particle, and what we're going to concentrate there is the photoelectric effect. Again, this is something I can do in class. It is dependent upon the weather, namely if you have high humidity, then you're out of luck. Okay, so if it's dry and warm, that's your best bet. Of late, we've had like 30% humidity, and we live close to the ocean here, so it's like next to impossible. But I have gotten it to work. At any rate, this caused a lot of consternation for physicists. It took many, many years for people to figure it out, and in fact, it sort of lays the groundwork for a field called quantum mechanics. And one of famous physicist Feynman said that if he's ever met somebody, well, if anybody says that they understand quantum mechanics, they really don't. Quantum mechanics is how things move at the very, very small level, and we understood it first in terms of electromagnetism. If you kind of understood it, we can use it as a tool, but to get our heads around it is to understand it in sort of a biblical sense is sort of really difficult. At any rate, the idea is this: consider that that electrons are particles. Okay, that's, you can cause electrons to run into things, and you can see that they smash into things and cause things to bounce around, just like you could, throw a tennis ball at a wall and it bounces off, or you can throw a tennis ball to somebody else and they can catch it, or it can bounce off, as well, baseball errors, right? Okay, so now shine light on that electron, and what happens to it? Well, not much, at least for the tennis ball. Now, for an electron, that's entirely different, and let me show you that right here. So this is called the photoelectric effect, and this is what Einstein actually got his PhD for. He didn't get it for relativity or gravity, he got it for this. Now, this is a step-by-step process. This is a piece of styrofoam, a styrofoam cup, to insulate the aluminum can from the table. So you have an aluminum can here that's taped to the styrofoam cup, and then you have a wire that's attached to the aluminum can, and then from the wire you hang tinsel from it. I have hung just a piece of aluminum foil that's cut, and it looks like kinky hair, and basically it makes my experiment not nearly so pretty. And what he's doing now is he's going to sand the top of the aluminum. Aluminum is used for beverage cans and for lots of tools and stuff like that because it doesn't rust. In reality, it rusts a few atomic layers, and those few atomic layers are so strong that they do not allow oxygen to penetrate the aluminum any further. So it creates an impervious layer that retards further rusting, and the device or the thing that you made is still intact and can be used for its original function. Contrast that to iron, say a nail, and you put it outside, it will rust into a bunch of powder, and obviously you can't use the nail to attach two boards together. I mean, it's just a bunch of powder. So he's now removing the top layer of aluminum oxide to expose the bare aluminum underneath. And the bare aluminum has a bunch of electrons floating around on it. You can calculate stuff by assuming that the electrons are free to move around in a gas. And what he's going to do is show you that he can charge up the aluminum can by rubbing this piece of paper on this piece of plastic and charge up this aluminum can. And you can see that because, remember, electrons are going to repel each other. These electrons are going to move all over this can and the wire and the tinsel, and since the electrons want to get away from each other so much, we'll see the tinsel spreading apart spread apart as much as they can. So it's going to, instead of hanging down, it's going to be spread out. So now he's charging up, he's creating some static charge, and now he's showing you that he can discharge the charge that's on the aluminum can. So it went through his body back down to the ground. Okay, so remember what's going on is we've charged up the aluminum foil and they spread out. Okay, and that shows you that we have charge there. Okay, now also notice that there is light impacting upon this can. All right, and the light that's impacting the can right now, the visible light, is not causing a discharge. Okay, the person had to touch the can and cause the discharge. And now he's charging it up again, and now he's going to bring an ultraviolet lamp, and notice what happens. Immediately, the foil started changing its position. Let me see if I can get back to it. Okay, so here we are. Immediately, right there, you saw it immediately, the foil, the charges were somehow disappearing, and he hadn't touched the can. Okay, let's see it again. So he opens it up, and then immediately you see it moving. There is no time lag. It immediately moved. Okay, so that's the photoelectric effect. And I've done this in class, and yes, and truly it works like this. So it's pretty amazing. The light is behaving as a particle. And the particles, the light has to be the right energy, otherwise it doesn't work. So, and there's no time lag between when you start the light on it and the observance of the motion of those aluminum hair, if you will. Okay. Now you can also find out that so first of all, the light ejects the electrons. Okay. But waves don't do that. Okay. The waves go through particles, and the more light you hit this thing with, then you'll create more of the same. Okay. Now, if low frequency light doesn't eject the electrons, okay, but the high frequency light does, okay. Now, the problems associated with this thing, that we would expect for waves is you could perhaps think of an idea of waves causing particles to move. And so the idea there I try to get across is, imagine that you're in a pool and you create a wave action in the pool, or maybe you're in a tub. You can create a wave action, and maybe the superposition of the waves as they're bouncing around back and forth between the sides of the tub, you can splash some water out. Now, naturally, you can cup water and splash it out. But let's just consider if you're creating a wave. Well, sometime in the future, you can create enough of a wave crest so it slops over the edge of the pool or the edge of the tub. Okay. What we saw with the experiment was an immediate reaction. Okay. And classical physics can't explain that. Okay. And then these other statements here that you see here are also problems that classical physics can't explain. So that's how we got into this really weird world of the quantum world. Okay. All right. So let's see. Yeah, these are some more charts that you can take a look at if you want. And so basically we came back to the idea that Newton had, which was light as a stream of particles. And the photons interact with matter one at a time. Okay, so high energy photons dislodge electrons from certain metals, and that energy of the photon, which is the particle name we give to light, hits the electron in this instance and knocks it for a loop. Okay, if the photon has more energy, then the electron gets knocked for a bigger loop. And if there is not enough energy, then the photon, and the electron don't even see each other. Okay, so basically, we have a bunch of different experiments that show that light behaves in all sorts of fun and interesting ways. Okay, it behaves as a wave, and then it behaves as a particle. Now, in the next section, hopefully I'll show you some gas tubes and show you how light behaves as far as identifying different elements, and talk about Wien's law and the Stefan-Boltzmann law. Now, there's one thing here that I have on this chart that I haven't been able to show you yet, and I'll probably will in the near future alter this video for that, and that's the Crookes radiometer. This is another example showing that light is behaving as a particle. You probably heard about the idea of solar sailing, and that's what we're talking about here. Crookes radiometer is basically something like that. If you look up on YouTube, you can see videos of this, that when light hits the radiometer, it causes the vanes of the radiometer to move. The vanes are in a partially evacuated chamber, and so there's really no way that a breath could cause the motion there. And if you put the radiometer in a dark room, then the wheels don't turn, the vanes don't move. But when you put it in sunlight, then it does. Okay, so where does that leave us? Basically, light behaves as a particle and a wave. And the best way I've heard to think about this fact is that as light travels from place to place, it behaves as a wave. And then finally, as it, when it arrives at its destination, or when it is been created, it behaves as a particle. And so with water waves, you can view that as the wave hitting the beach. Okay, and the energy of the wave gets dissipated on the shore. Okay, thank you very much.